Hi, my name is Pablo, and I am very excited today to be talking to you about chloride-induced corrosion of steel reinforcement in alkali-activated slag metakaolin concretes. Now, this is a project I have been able to work on as part of my research fellowship at the University of Leeds. This work actually was performed by Professor Susan Bernal and has been advised and supervised throughout the duration of my fellowship. So with that, I would like to start with the motivation. And the motivation for this study was really the limited understanding that we have on corrosion mechanism of alkali activated concretes, specifically the long-term behavior of corrosion in these materials. So to introduce the topic, we're going to be looking at the properties of alkali activated concretes and how those may be affecting their durability, some of the important parameters for the durability of these materials. The research results are going to focus on three main aspects. The first aspect is about corrosion potential as it changes over time. The second aspect is going to be the corrosion resistance, or RP, and how that changes over time. And lastly, would look at validating the RP values that we get from linear polarization resistance, which we'll talk about, and electrochemical impedance spectroscopy, or EIS. One of the biggest lessons that we have learned from this project is that a good understanding of corrosion mechanisms in alkali activated concretes can be really heightened by coupling non-destructive electrochemical techniques. And the two main ones that we're going to focus on today are LPR and EIS. We'll finish this presentation with some conclusions per usual. Now, in the motivation, I talked about corrosion. And as we all know, corrosion is one of the major worldwide infrastructure challenges. And just to give you a little picture, I know this is probably a fact that many of you know, but about 1.8 trillion pounds globally are spent every year trying to prevent, mitigate, and repair civil infrastructure damage by corrosion of the steel reinforcement. This is about 3.4% of the global GDP, so very large and significant economical cost to this durability issue. Alkali activated materials, or AAMs, have been proposed as possible durable material solutions that can be part of a toolkit of concrete technologies. Now, the aspects that make these materials interesting for the durability perspective is that they tend to have a lower chloride diffusivity, higher chloride binding, and low conductivity in their pore solution. Now, of course, these aspects and material properties depend on the formulation of alkali activated materials. However, in general, our understanding remains pretty limited when we're considering corrosion mechanisms, and this is because we don't have a lot of long-term studies to understand how the long-term exposure can change the corrosion mechanisms and the behavior of the material. Relatedly, a way to reliably assess corrosion mechanisms and processes is often lacking. So to start off, I'd like to describe the material that we used, and this material is a slag with 10% metakaolin that we have activated to create the alkali activated concrete. Now, we have achieved a silicon to aluminum ratio of 2. One thing to note about this silicon to aluminum ratio is that it denotes the bulk silicon to aluminum ratio and not that of the cementitious binder that composes it. We have used a sodium silicate solution with sodium hydroxide solution. Now, the sodium silicate solution had a silicon moduli of 2.4, and the sodium hydroxide solution was composed of 50% weight sodium hydroxide. Now, these two solutions were combined to create the alkali activator, and in total the mixture had a sodium oxide content of 11.6 weight percent. Now the specimens were cured at a relative humidity of 90% at room temperature for 28 days prior to testing. All the materials, all the specimens, had a reinforcement embedded into the material. This was a carbon steel reinforcement, and it was coated with an epoxy paint to control the amount of surface area embedded inside the material that was exposed to the material itself. This surface area was 9.97 centimeters squared. Now, all the specimens were then immersed in 3.5 weight percent sodium chloride solution for a total duration of 335 days, and they were also tested at 64, 158, 276, 335 days. The research aim that this project aims to answer is what is the long-term corrosion behavior of these alkali-activated concrete materials when exposed to chloride ions. Now, in order to answer this research question over time, two main electrochemical techniques have been employed. The first one is linear polarization resistance. This is a direct current, or DC, polarization technique that is non-destructive. Now, the reference electrode that was used was a silver chloride electrode, and the counter electrode that was being used, it was an external graphite bar. Now you can see a schematic on the right of this slide that can show you how the graphite external bar is surrounding the concrete sample, and you have the silver chloride reference electrode on the outside touching the surface of the sample. Now the scan rate was kept pretty low, and this is to prevent any disruptions to the surface of the working electrode or the reference, the reinforcement bar, excuse me. And the sample period was 2 seconds. 2 seconds per sample. Now, electrochemical impedance spectroscopy, or EIS, is an AC alternating current technique that is non-destructive as well. And it was the same setup was used with the reference and counter electrodes, and the polarization window is a bit smaller than that of the linear polarization resistance at 10 millivolts. The frequency range was full sweep from 0.1 megahertz to 10 millihertz, and the sample size was 3 points per decade. So to start off with the results, here we have the corrosion potential, or OCP, values that have been collected over time being in the x-axis. And at 0 days, it's really important to note that at 0 days, the value that was obtained was much higher than the oxygen evolution potential, which is at negative 198.5 millivolts. So this value over here is indicating that the samples are not fully saturated at this point, right? These are samples that have been just cured, and the OCP potential has been measured. So after immersion in sodium chloride solutions, one can observe that the values of OCP have decreased and have a generally decreasing trend. Now, the fluctuations in these values indicate that there is just changes to the reinforcement bar's surface chemical composition as described by the Nernst equation, which means that there are chemical changes happening over time. To understand what these chemical changes are and how important they are, so when we're looking at the RP values derived from linear polarization resistance, we can see that in the initial 158 days of sodium chloride exposure, there is an increase in RP values, likely indicating that the steel corrosion resistance is increasing due to the formation of perhaps a layer. And the local maxima here is at 158 days. Now, after 158 days, we see that there is a sharp decrease in RP values, likely indicating that there is a breakdown of a protective layer. Hence, the results really suggest that after 158 days, there may be an onset of corrosion initiation in these materials. To further probe and validate what's happening specifically at 158 days, this graph right here is showing the EIS data from these materials at 158 days. What we can see is that the model that we have chosen here that makes physical sense is a well-fitted model. It makes physical sense because we hypothesize that there is a porous film intermediate in the steel concrete interface. Now, from this model and this hypothesis, we can actually understand that the high corrosion resistance that we observe is a composite of two main physical entities. One is the metal corrosion resistance of the reinforcement, and then the other is that of the impedance of a porous intermediate film. To conclude this presentation, there's a few remarkable results that we want to highlight, and that is that after chloride immersion and increased exposure time, we have seen the fluctuation of corrosion potential values, and these may indicate the activity that is happening at the working electrode or reinforcement bar's surface. We have seen that after 158 days, chlorides begin to initiate the corrosion at the steel concrete interface, as it is likely indicated by a sharp decrease in the corrosion resistance. Now, this corrosion resistance, we have seen that EIS hypothesizes with our model that it's composed of two main things. So first is the corrosion resistance of the working electrode or the reinforcement bar, and then the next is the impedance developed by the intermediate film that is at the surface of this working electrode. When we start to think about the outlook for research needs, really need long-term studies above or higher than 90 days to comprehensively evaluate what is actually happening to the corrosion of embedded reinforcement in these alkali activated concrete materials. So I would like to acknowledge first the European Commission for providing the funding for me to develop and analyze the data of this project under the Marie Curie Fellowship grant scheme, and also the University of Leeds, and specifically Professor Susan Bernal, because without her guidance and the opportunity to look at this project, I wouldn't be able to have done any of this. So thank you very much. And with that, I would like to open for any questions that the audience may have. Thank you so much for your attention.